This presentation brings together two of the most foundational frameworks in all of physics: quantum versus classical mechanics, presented by Dr. Induru Jagadish. What follows is a rigorous comparative analysis of these two paradigms, exploring where they agree, where they diverge, and why that distinction matters profoundly across science and technology. Let us begin. To frame our analysis, let's establish the two frameworks we'll be comparing throughout this presentation: classical physics and quantum physics. On the classical side, we have what we might call the world of the large. Classical mechanics governs macroscopic objects, planets, cars, humans, essentially everything we can observe with the naked eye. The key figures who shaped this framework are Isaac Newton and James Clerk Maxwell. Its core concepts rest on two foundational pillars. The first is determinism. Knowing the current state of a system allows for perfect prediction of the future. The second is certainty. Objects have definite positions and velocities at all times. In the classical world, there is no ambiguity. If you know where something is and how fast it's moving, you can calculate exactly where it will be. Turning now to the right side of our comparison, quantum mechanics describes the world of the small, governing subatomic particles such as atoms, electrons, and photons. The key figures here include Max Planck, Albert Einstein, and Werner Heisenberg, whose groundbreaking work in the early 20th century fundamentally challenged classical assumptions. The core concepts of quantum mechanics stand in sharp contrast to their classical counterparts. Rather than certainty, quantum outcomes are probabilistic. They are based on mathematical likelihood, not certainty. And rather than continuous energy, quantum mechanics introduces the concept of quantization. Energy is not continuous. It comes in discrete packets known as quanta. This side-by-side comparison sets the stage for understanding why these two frameworks, while both describing the physical world, operate under entirely different rules. One of the most fundamental distinctions between these two frameworks comes down to a concept we can call key differences: determinism versus probability. On the classical side, the universe operates in a fully predictable, deterministic way. If you kick a ball, you can calculate exactly where it will land. Given the initial conditions, the force, the angle, the velocity, Newton's laws give you a precise, definitive answer. There is no ambiguity. Quantum mechanics, however, operates on an entirely different set of rules. At the subatomic level, you cannot know exactly where an electron is. Instead, you only have a cloud of probability where it might be. This isn't a limitation of our instruments or our measurements. It is a fundamental property of nature itself. The electron doesn't have a single fixed location until it is observed. It exists as a spread of possibilities. This shift from certainty to probability is perhaps the most profound conceptual leap between classical and quantum mechanics, and it underpins nearly everything else we will explore going forward. Building on those foundational differences, one of the most striking conceptual departures between classical and quantum mechanics is the phenomenon known as wave-particle duality. From the classical view, light is a wave and matter is a particle. They are distinct categories. A beam of light behaves like a ripple on water, while a billiard ball behaves like, well, a billiard ball. The two simply do not overlap. The quantum view, however, dismantles that clean separation entirely. In quantum mechanics, everything has both wave-like and particle-like properties. An electron, a photon, even an atom. Each of these can exhibit characteristics of both a wave and a particle depending on the context. Perhaps the most compelling demonstration of this is the double-slit experiment. It demonstrates that particles, like electrons, can interfere with themselves like waves, producing an interference pattern on a detector screen. But here is where it becomes truly remarkable. That wave-like behavior persists only until they are observed. The moment a measurement is made to determine which slit the particle passed through, the interference pattern disappears, and the particle behaves as a classical particle once again. This is the observer effect in action, and it sits at the very heart of quantum strangeness. Building on those core conceptual differences, one of the most striking distinctions between the two frameworks concerns the role of the observer. In classical physics, measuring a system does not change its state. A simple analogy makes this clear. A thermometer doesn't change the weather. The act of measurement is passive. It simply reads what is already there. In quantum physics, however, the act of observation itself collapses the wave function. The very moment you measure a quantum system, you fundamentally alter it. This is not a limitation of our instruments. It is a property of nature at the subatomic scale. This idea is perhaps best illustrated by Schrödinger's cat, a thought experiment illustrating how a particle can exist in multiple states, known as superposition, until someone looks at it. The cat in the box is simultaneously alive and dead until the moment of observation forces it into one definite state. It sounds paradoxical, but this is precisely how quantum systems behave. Turning now to practical applications, these theoretical differences translate into very real and distinct technologies. On the classical side, the applications are the large-scale engineering achievements we rely on every day. Structural engineering, including the bridges and buildings that define our cities, and aerospace, including the remarkable feat of sending rockets to the moon. Quantum applications, on the other hand, operate at the microscopic level but have equally profound real-world impact. Semiconductors, the foundation of your smartphone and computer, are a direct product of quantum mechanical understanding. So too are MRI machines and lasers, technologies that have transformed medicine and industry alike. In short, both frameworks are not merely theoretical. They are the engines behind the physical world we engineer and inhabit. Bringing this into the realm of chemistry, the difference between classical and quantum chemistry essentially comes down to how we model the glue that holds matter together, the electrons. Starting with classical chemistry or molecular mechanics. This approach treats atoms like billiard balls connected by springs, where those springs represent the chemical bonds between them. It uses Newton's laws to calculate how molecules move and vibrate. Crucially, it doesn't actually look at electrons at all, it simply models the forces they create. It's an efficient, large-scale approximation. Quantum chemistry, on the other hand, focuses entirely on the behavior of electrons. Rather than abstracting them away, it uses the Schrödinger equation directly to determine electron density, orbital shapes, and energy levels. This is a far more rigorous and computationally demanding description of molecular structure. So, the core distinction is this. Classical molecular mechanics sidesteps the electrons to gain computational speed, while quantum chemistry confronts them head-on to gain fundamental accuracy. These differences become even more pronounced when we look at two critical areas: electronic structure and computation and scale. Starting with electronic structure. In the classical view, bonds are fixed or have a set ideal length. Critically, it cannot explain how a bond breaks or forms, because it doesn't account for electron rearrangement. The electrons are essentially invisible to the model. The quantum approach, by contrast, treats bonds as dynamic. It explains why atoms bond by calculating the probability of finding electrons between nuclei. And because of this, it is essential for studying chemical reactions, where bonds are actively breaking and forming. Now, this added depth in the quantum model comes at a significant cost, which brings us to computation and scale. On the classical side, simulations are very cheap computationally. You can simulate massive systems, like an entire protein or a virus, containing millions of atoms. This scalability is one of classical mechanics' greatest practical strengths. On the quantum side, however, calculations are very expensive and complex. They are so computationally intense that they are usually limited to smaller molecules or specific fragments of a larger system. So there is a fundamental trade-off. Quantum mechanics gives us greater accuracy and chemical insight, but classical mechanics gives us the scale to tackle biological and material systems of real-world size. This brings us to one of the most practically significant distinctions between these two approaches, and that is predictive power. On the classical side, the model relies on what are called force fields, parameters based on experimental data. In other words, the classical model has been trained, so to speak, on molecules that scientists have already studied and measured. The critical limitation here is this. If you haven't seen a specific type of molecule before, the classical model might guess wrong. It simply doesn't have the reference data it needs to make a reliable prediction. The quantum approach, by contrast, operates under an entirely different philosophy. It is ab initio, a Latin phrase meaning from first principles. And what makes this so powerful is that it doesn't need experimental data to make predictions at all. Instead, it calculates molecular properties based purely on the laws of physics. No prior observations required. This is a fundamental distinction in how each framework handles the unknown. Classical mechanics is, in a sense, interpolating from what it already knows. Quantum mechanics is deriving answers from the ground up, making it far more generalizable, particularly when exploring novel or previously uncharacterized chemical systems. With those distinctions in mind, let's consolidate everything into a direct comparison summary, placing classical chemistry and quantum chemistry side by side across 5 key features. Starting with how atoms are treated. In classical chemistry, atoms are modeled as hard spheres, essentially balls, while quantum chemistry treats them as nuclei embedded within an electron cloud. That shift alone represents a fundamentally different physical picture. Moving to bonds. Classically, bonds are treated as springs, mechanical connections that stretch and compress. In quantum chemistry, bonds are understood as shared electron waves, a description rooted in the probabilistic nature of quantum mechanics. The key equations reflect this divide clearly. Classical chemistry is governed by Newton's F equals mr, force equals mass times acceleration. Quantum chemistry, by contrast, is governed by the Schrödinger equation, H psi equals E psi, where the Hamiltonian operator acts on the wave function to yield the system's energy. When it comes to what each approach is best for, classical methods excel with large proteins and polymers, systems too vast for quantum treatment. Quantum chemistry, on the other hand, is the method of choice for small molecules and reaction mechanisms, where electronic detail is essential. And finally, the main limitation of each. Classical chemistry cannot model bond breaking since it has no electronic description. Quantum chemistry, while far more rigorous, is extremely slow for large systems. The computational cost scales steeply with system size. This table captures the core trade-off: physical accuracy versus computational feasibility. Neither approach is universally superior. The right tool depends entirely on the question being asked. At the heart of quantum mechanics lies one of the most fundamental equations in all of physics, the Schrödinger equation, and specifically here, its time-dependent form. On the left side of the slide, we see the equation itself, I times h bar multiplied by the partial derivative of psi with respect to time equals the Hamiltonian operator acting on psi. Let's break down what each of these symbols represents. The I is the imaginary unit, a mathematical construct essential to describing quantum wave behavior. H bar is the reduced Planck constant, which sets the scale of quantum effects. Psi, written as the Greek letter psi, is the wave function, the central object in quantum mechanics that encodes all the probabilistic information about a system. The T represents time, and finally, H hat is the Hamiltonian operator, which represents the total energy of the system. Together, this equation tells us how the wave function of a quantum system evolves over time. Unlike classical mechanics, where we track the precise position and momentum of a particle, here we are tracking the evolution of a probability amplitude, a fundamentally different and more abstract description of physical reality. This equation is the quantum mechanical analog of Newton's second law, but operating in the probabilistic, wave-like world of the subatomic. Now, let's look at the mathematical structure of the Hamiltonian more concretely. In its most basic form, the Hamiltonian is the sum of the kinetic energy operator, T hat, and the potential energy operator, V hat, giving us the elegant expression, H hat equals T hat plus V hat. Taking this a step further, for a single particle of mass m moving in 3 dimensions, the standard non-relativistic Hamiltonian is expressed as H hat equals negative h bar squared over 2m multiplied by the Laplacian operator plus V of r. Each term in this expression carries precise physical meaning. H bar represents the reduced Planck constant, that fundamental quantum of action that sets the scale of quantum effects. The Laplacian operator, del squared, captures the second spatial derivatives, encoding how the wave function curves through space and giving rise to the kinetic energy contribution. And finally, V of r is the potential energy function, which depends on the position of the particle within the system. Together, these components form the complete quantum mechanical description of a particle's total energy, a far cry from the simple classical sum of kinetic and potential energy, now recast in the rigorous language of operators acting on quantum states. Building on the Hamiltonian's identity as a Hermitian operator, let's now examine its role in the Schrödinger equation, which brings us to point 2. The Hamiltonian is the central component of the Schrödinger equation, which governs how quantum systems behave. This manifests in 2 critical forms. First, the time-independent Schrödinger equation. This is an eigenvalue equation where the energy, E, is the eigenvalue associated with the wave function, psi. Mathematically, this is expressed as H hat acting on psi equals E times psi. In practical terms, solving this equation yields the allowed energy levels of a quantum system, the discrete quantized states that have no classical analog. The second form is the time-dependent Schrödinger equation. Here the Hamiltonian also dictates how a wave function evolves over time. The equation reads H hat acting on the full wave function, psi of r and t equals I times h bar times the partial derivative with respect to time of psi of r and t. This formulation is more general. It captures the dynamic evolution of a quantum state, not just its stationary energy levels. Together, these 2 equations demonstrate why the Hamiltonian is so foundational. Whether we are asking what energies a system can have or how it changes through time, the Hamiltonian is always at the center of the answer. Now that we've established what the Hamiltonian operator is, let's examine its key properties and why each one matters physically. The first and perhaps most fundamental property is that the Hamiltonian must be a Hermitian operator, meaning it is equal to its own conjugate transpose. This property ensures that its eigenvalues, which represent the measured energies of the system, are always real numbers. This is not merely a mathematical convenience, it is a physical necessity. After all, any energy we measure in a laboratory must be a real, tangible quantity, not a complex one. Building directly on that, the set of all possible eigenvalues of the Hamiltonian is what we call the energy spectrum of the system. Think of it as a complete catalog of every energy level the system is permitted to occupy. Depending on the system, this spectrum may be discrete, as in the quantized energy levels of an atom, or continuous. Finally, there is the property of time evolution. In quantum theory, the Hamiltonian is known as the generator of time evolution, meaning it determines the future state of a system based on its current state. In other words, if you know the Hamiltonian and the present quantum state, the Hamiltonian governs precisely how that state will evolve forward in time, a role that echoes yet fundamentally differs from the deterministic equations of classical mechanics we examined earlier. Turning now to the core quantum computing concepts, it's worth understanding precisely what makes quantum machines so fundamentally different from their classical counterparts. Quantum computers leverage two phenomena that classical machines simply cannot replicate. The first is superposition. This allows a qubit to represent a combination of states simultaneously. To put that in concrete terms, 3 classical bits can represent one of 8 numbers at any given moment. 3 qubits, however, can represent all 8 simultaneously. That distinction alone hints at the extraordinary computational potential quantum systems carry. The second phenomenon is entanglement. This links qubits so that the state of one instantly influences another, regardless of distance. This interconnection allows for highly coordinated calculations that would be impossible to achieve through classical means. Together, superposition and entanglement form the foundational pillars upon which quantum computing is built, and they represent a decisive departure from everything classical mechanics can offer. With that conceptual foundation in place, let's bring it all together with a direct side-by-side comparison. Key differences at a glance. The two systems operate on fundamentally different physical principles and are suited for different types of tasks. Starting with the basic unit of information. In classical computing, that unit is the bit, a definite state of either 0 or 1. In quantum computing, the equivalent is the qubit, a probabilistic state that can be 0, 1, or both simultaneously. Moving to logic, classical computing is deterministic, following precise if-then steps using transistors. Quantum computing, by contrast, is probabilistic. It uses quantum waves and interference to find solutions. When it comes to processing, classical systems are sequential, handling tasks one after another, or in simple parallel chains. Quantum systems are simultaneous, exploring many possible solutions at once through the phenomenon of entanglement. Considering memory, classical computing offers persistent and cheap storage. Data is stable and easily copied, as we see with SSDs and cloud systems. Quantum memory, however, is fragile and limited. States cannot be copied and will collapse if disturbed, a phenomenon known as decoherence. Finally, on the matter of errors, classical systems have a low error rate, making them highly stable and easy to correct. Quantum systems carry a high error rate, as they are extremely sensitive to heat and noise. Taken together, these 5 dimensions, basic unit, logic, processing, memory, and error handling, paint a clear picture of why these two paradigms are not in competition, but rather suited to fundamentally different classes of problems. Let's consolidate everything we've covered into a concise summary table, placing classical mathematics and quantum mathematics side by side across 6 key features. Starting with foundation, classical mechanics is built upon Newton and Maxwell's calculus, while quantum mechanics rests on Schrödinger and Heisenberg's linear algebra. These are fundamentally different mathematical languages describing fundamentally different realities. Moving to values. In the classical world, quantities are continuous and smooth, varying seamlessly across a range. In the quantum world, values are discrete and quantized, existing only in specific permitted states. When it comes to predictability, classical mathematics is deterministic and definite. Given initial conditions, outcomes are fully predictable. Quantum mathematics, by contrast, is probabilistic and random. We can only speak in terms of likelihoods. Regarding system state, classical mechanics describes a system using coordinates, position x and momentum p. Quantum mechanics replaces this with the wave function, psi, which encodes all probabilistic information about a system. On the question of combination, classically, states combine additively, as in simply adding velocities v1 plus v2. Quantum mechanically, states combine through superposition, a weighted sum that allows a system to exist in multiple states simultaneously. And finally, logic. Classical systems operate on Boolean logic, a binary world of true or false. Quantum systems, however, are governed by the mathematics of Hilbert space and matrix operations, enabling a far richer and more complex logical structure. Taken together, this table makes clear that the shift from classical to quantum mechanics is not merely a change in scale. It is a profound transformation in the very mathematical framework we use to understand nature. So, why are they different? At the most fundamental level, the distinction comes down to the domain each theory is designed to describe and the mathematical language each one speaks. Quantum theory is fundamental and applies to the microscopic world where energy levels are separated, where particles exist in discrete states and transitions between those states are quantized. Classical mechanics, on the other hand, is an approximation derived for large-scale, everyday objects where these discrete jumps are undetectable. At the scale of billiard balls and planets, the granularity of quantum behavior simply averages out, and classical descriptions work perfectly well. This difference in domain is also reflected in their mathematical structures. Classical mechanics frequently uses real numbers in vector calculus. Familiar tools like forces, velocities, and trajectories described through continuous, real-valued functions. Quantum mechanics, however, relies on a far more abstract framework. Linear algebra, complex numbers, Hermitian operators on Hilbert spaces, and commutation relations. These are not merely more complicated versions of classical tools. They represent a fundamentally different way of encoding physical reality. One where observables are operators, states are vectors in an abstract space, and the act of measurement itself is built into the mathematics. Understanding this distinction in both scope and mathematical structure is essential before we can meaningfully compare how these two frameworks are applied in practice. The expression bracket xp bracket equals IH bar is known as the canonical commutation relation, the fundamental mathematical bridge between classical and quantum mechanics. It is precisely this relation that defines why the quantum world is probabilistic rather than certain. To understand where this comes from, let's start with the math, specifically the concept of non-commutativity. In classical mathematics, order simply doesn't matter. 3 times 5 equals 5 times 3, And so x times p minus p times x equals 0. Multiplication is commutative. You always get the same result regardless of the order. But in quantum mechanics, x representing position and p representing momentum are not just numbers. They're operators, mathematical objects that act on quantum states. The bracket notation, bracket x, p bracket, is a shorthand called a commutator, and it is defined as x times p minus p times x. Now here is the critical point. The fact that this commutator equals ih bar, a non-zero value, means that the order in which you apply these operations genuinely matters. If you measure position first and then momentum, you get a fundamentally different result than if you measure momentum first and then position. This is not a limitation of our instruments. It is a deep, irreducible feature of nature itself, encoded directly in the mathematics. Now, this brings us directly to the physics, specifically the uncertainty principle. That mathematical leftover, the term IH bar, is directly responsible for the Heisenberg uncertainty principle. And to understand why, we need to look at what each of those two components actually means. First, h bar, the reduced Planck constant. This sets the scale of the quantum world. Because it is an extraordinarily small number, we simply don't notice these quantum effects in our daily life. At the macroscopic scale, they are effectively invisible to us. Second, the imaginary unit, I. Its presence ensures that the operators in quantum mechanics are Hermitian, meaning they correspond to real, physical observables. In other words, even though the mathematics involves imaginary numbers, the quantities we actually measure in the lab are always real. The imaginary unit is not a mathematical curiosity. It is a structural requirement that keeps the theory physically meaningful. So these two constants, working together within that single term, are what give rise to one of the most profound and counterintuitive results in all of physics: the fundamental limit on how precisely we can simultaneously know certain pairs of properties, like position and momentum.